Now that we're done checking whether the table is degenerate or non-degenerate, and this time we were able to check that it is indeed a non-degenerate, then right now we are going to check whether the solution that we have is optimal or not. And to check that, we will be using the stepping stone path method. So stepping stone method will start with the first step, which we are going to select any vacant squares or any unused square. This time um, we have 1, 2, 3, 4, 5, 6 vacant squares, and we will just select any of these six. But this time for this video, we are going to select this cell or the square DX. Okay, so for the second step, now that we have selected square dx, we are going to trace a loop using use squares or using occupied cells, starting from the selected unused square, and then leave alternating negative and plus signs as you step on the squares. So starting from dx, we have here positive 4. That's the first sign that we will put in. We are going to step either to the left or to the bottom part as long as that cell or that square is occupied. So since both the cell CX and both DY have occupied cells, then we can step on those cells. So we will start with DX and then to CX. This time we are going to leave a negative sign. Now after that square, we will be going down, and then we will leave positive symbol or positive sign, and then to the right and the negative symbol, and then to the original square. So we are making a loop right here, making sure that we are able to go back to the original square, which is the dx. So for this loop, we will be calculating the improvement index. So dx, positive dx minus cx plus cy minus dy is equal to positive 4 minus 2 plus 4 minus 3 is equals to 3. So since the improvement index is positive 3, then that means that we don't need to do any revision for this particular loop, meaning it is good to go. Now we are going to check the rest of the vacant squares. So this time we will check AY, this particular vacant square. We are going to make a loop around this square. So this is the loop that we have created from AY to AX, and then step directly to CX, and then CX to CY, and then back to AY. So we have positive AY minus AX plus CX minus CY equals 4 minus 2 plus 2 minus 4, and that is equal to 0. So since we have a 0 index still, then we don't need to make any revision for this particular loop. Now that we're done with AY route, we can choose any other vacant square. This time we are going to select BY route. So don't forget, guys, that whenever you step on a particular vacant squares, we need to leave alternating signs. So positive, negative, positive, negative. So for the BY route, so from BY, we go to the BX, and then CX, and then CY. So that would be 6 minus 2 plus 2 minus 4 is equal to 2. And again, we have a positive index. That means that we don't need to make any revisions for this particular loop. So on to the next route, we will check the AZ route. So AZ, we go to AX, and then CX, and then CY, and then DY, and then DZ, and then back to AZ. So we have here positive AZ minus AX plus CX minus CY plus DY minus DZ, and that would be equal to 2. And again, we have a positive index right here. Next vacant cell would be BZ. So BZ to BX to CX, and then to CY to DY, and then to DZ. So take note, guys, that the only vacant cell in the route will be the original square. The rest will be an occupied cell or square. So we have here 2 minus 2 plus 2 minus 4 plus 3 minus 0, and that is equal to 1. And again, we have a positive index. So on to the last route, we have the ZZ route. So ZZ to CY, CY to DY, and then DY to DZ, and then back to CZ. So the answer for the improvement index would be 1 minus 4 plus 3 minus 0, and that is 0. And again, we have a positive index right here, or 0. So that means we don't need to improve the said table. So now that we have checked all the possible vacant squares, and we are also able to determine that if not positive, we have a 0 index. So that means the initial solution is actually an optimal solution as well. So here, since the entire resulting improvement index is positive, we have already reached the optimum solution. And for the given example, the initial solution is also the optimal solution. So as you have noticed, the table right here, the units have been changed to the original profit. So see the difference. In this previous table, we are using the unit that we have deducted from the maximization to minimization. Now on the next table, we are now using the original unit cost right here. So all we have to do for us to determine the maximum profit that this particular problem is would be, we have to multiply 6 times 150 plus 6 times 130 plus 6 times 30 plus 4 times 90 plus 5 times 10, and then plus 8 times 290, and that is equal to $4,000 590. That means that for factory X must deliver 150 units to dealer A, 130 units to dealer B, 30 units to dealer C. And factory Y should deliver 90 units to dealer C, 10 units to dealer D, and 290 units to dealer. Factory Z must deliver 290 units to dealer D in order to have a maximum profit of $4,590.